Dymola is capable of simulating dynamical systems over a wide range of domains, including mechanics, electronics and thermofluid analysis. The package browser to the left shows all the available building blocks. Looking inside the electrical package, we find several sub-packages dedicated to different domains. There are packages for analog and digital components, built-in models for machines such as electrical motors and transformers, multi-phase systems, as well as power converters. Within the analog sub-package, there is a collection of basic components, idealized components, transmission lines, semiconductors, as well as voltage and current sources. Now, let's build a model of a low-pass filter using the components in the analog package. Components are inserted through a drag-and-drop maneuver. First, we define a ground. We can easily manipulate the size and position of a component icon. We will add a pulse voltage source next. After rotating the icon, we double-click it to edit the component's properties. The amplitude, duty cycle, and period time of the pulse voltage signal are set here. To connect two components, we select a pin on any component, displayed as a square. The connection is finished by dragging it to another pin. Next, we add an idealized operational amplifier. Again, we set the properties of the op-amp by double-clicking it. We'll use the default values for the supply voltages and no load gain. We connect the op-amp to ground, and continue by inserting a resistor. In the dialog, we set the resistance of the resistor. We now add a second resistor to the circuit. We flip its icon, and likewise set its resistance in the dialog after double-clicking. As a next step, we include a capacitor in the model. We enter the dialog once again, in order to set its capacitance. When entering a quantity, we may choose the unit in which to specify it. Unit conversion is conveniently handled by Dymola in the background. After connecting all the present parts, our model of a low-pass filter is completed. Suppose that we want a visual indicator of the op-amp's output signal. A voltage sensor will be inserted for this purpose. In order to display the voltage, the sensor is complemented with a show component. We connect these to the rest of the system, and all that remains is then to initialize the model. Initial conditions for a component are set in the same dialog as the other properties for that component. In our case, we set the initial voltage drop over the capacitor to 0. If we desire to examine a component in the model more closely, we can do so at any time. Open Class takes us to a diagram view of the component. While viewing a class, we can conveniently switch to its coding layer or its documentation to retrieve desired information. By using the tabs feature, we can instantly return to viewing the model. So far, we have demonstrated how to build a simple model with a predefined input signal, though modeling in Dymola supports general expressions which depend on time and state variables. From the examples library included with Dymola, this is a more complex model of a DC-PM motor connected to a cooling system, demonstrating the possibility to model interactions between the thermal, electrical and mechanical disciplines. Let's go back to our model to simulate it. We will switch to the Simulation tab, and then enter the simulation settings. We set the simulation time to 1 second, and use the default solver algorithm. The Simulate button fires the simulation. In the browser on the left, the components of the model are listed. Expanding an item shows all quantities associated with that component. Every variable has a box next to it. Checking a box plots the variable, for instance the input voltage. Keep multiple boxes checked to plot several variables. Let's add the output voltage. We may view an animated diagram of the circuit at any playback speed. Remark that the output voltage changes over time. Suppose that we're interested in the effects of different capacitances. To change a parameter in the model between runs, we simply edit its value in the variable browser, and press the Simulate button once more. After running the simulation, the plot was instantly updated to reflect the new results.